Join us in this video where we present PounderPress and illustrate a new approach to bullet seating measurement. In this video, we'd like to tell you what PounderPress is and how to use it, talk about the bullet seating profile, provide a couple of examples, and then focus in on cartridge case annealing as a case study, and then wrap up with new proposals for measuring bullet seating. PounderPress starts with the K&N Precision Arbor press. On this is added a 220 pound force digital force gauge. EDMS is the data acquisition software. We didn't have to make any permanent changes to the press and can return it back to stock configuration. We need a window-based PC running i3 or better, and then the Wilson chamber type seating dies are critical to this setup. What we're going to do is measure a compression force while we're seating bullets. The force gauge sends real-time data over to the PC via USB. The data acquisition software records force time data and plots it graphically, and this is used for a broad range of reloading applications. PounderPress is part of our bullet seating workstation. Here's the laptop, here's PounderPress. You can see the USB connection. Here's a disassembled Wilson die, and we're ready to load 6.5 Creedmoor. This is an insert depth measurement setup. It starts with the Sinclair bullet sorting gauge. We use the digital plunger type indicator gauge, and we upgraded this to handle the extended die measurements. And over here, this is for coal measurement. This is a 6-inch digital caliper on an indicator base, and we start with the Sinclair insert style bullet comparators. Let's take a closer look at bullet seating and using the 223 Remington as an example. This is the seating force coming down here. We call it the drift force. In material sciences, this is called compression with interference. It involves both static and kinetic forces. Bullet diameter, 224 thousandths. The finished outside diameter of the case is 253 thousandths. So as you do the math here, we come up with a wall thickness of 14.5 thousandths. We're going to start with 221 thousandths on the ID, and we're going to finish with 224 thousandths. So you do the subtraction, and we have the characteristic 3 thousandths neck tension. In the material sciences, when you put a drift in, engagement depth is usually what's being talked about. But for reasons, as you'll see in a bit, we prefer to call this insert depth because it's very possible that the bullet's going to go in deeper than just the neck. Last but not least, here's the kind of things you'll see as materials for bullets. There's all the jacketed bullets, and when you see it presented this way, the first number is the percentage of copper, and the second is the percentage of zinc. Commercial bronze, copper gilding, these generally have lead cores. You might also have monometal type bullets, and then there's all the things that you use for lead alloys, whether it's lubricated, high-tech coating, or electrocoating. All of these things need to be considered when you start to take a look at what's involved with bullet seating. Here's a general overview of our test procedure. This varies a little bit depending on the type of test being done, but we always follow our cartridge case preparation baselining procedure. You can view the Pounder Bath Part 1 video to learn a lot more about that. At the sample prep station, the prime and charged case is put on the Wilson die base. We place the die body over the case and onto the die base. Add the bullet from the top and carefully place the seating stem, what we call the drift pin. At the measurement station, we measure the insert depth of the assembled die on the test stand. At PounderPress, we load the assembled die onto the press base, lower in contact the top of the drift, set 0, press start of the PC, and slowly lower the press arm. When the drift bottoms out, we press stop on the PC. The software will center and scale the seating profile, and we save the data and screen graphic. Here's the Wilson die loaded and ready to go on the insert depth measurement stand. We're actually going to measure the depth that's going to be inserted into the case, but this varies with each sample. The reason for this, it depends on the bullet bearing length, the bullet tail profile, the heel, the exact case trim length, how the drift stem profile fits into the bullet ogive, and then also the mouth chamfer. And we also need to be careful to monitor whether or not the bullet actually yields under the seating force. Here's a short video showing the bullet seating operation on PounderPress. Sample is ready for seating. Load, down the RAM, set 0, start acquisition, done. Here's the finish round on the Cole measurement station. Most reloaders are very familiar with this measurement. We set this up with a reference standard. We want to measure the cartridge overall length, but a lot of times the knee play of the bullets aren't uniform. So once we've got a good measurement of Cole, we use this setup to measure from the ogive to the base for more accurate measurement. By using the indicator stand, we have a very solid base, and the vertical setup reduces wobble, making it easier and faster for a reproducible measurement. This is what we call the bullet seating profile. Along this axis is time, and the y-axis is force in pounds force. When we first start applying the force, there's no movement of the bullet into the case neck. That's what we call static drift force, and that continues to increase without bullet movement up to a point where the mouth finally yields at drift FX max. You'll see a force drop. In this section, we are now dealing with kinetic drift force, and this increases as the bullet is seated into the neck. We finally get to a point of drift FK max, where it reaches the bottom of the neck, and we now have another drop in force. This plateau section here is just the kinetic force of friction as the bullet bearing surface just slides through the brass. The brass isn't yielding anymore, and this is very similar to your high school physics friction experiment. Finally, we get to the bottom where the drift bottoms out, and we get a bit of a spike. This is the insert depth we measured earlier. So from the time the brass finally opens up to the point it hits the bottom of the drift, that's what we're calling insert depth. Here's the seating profile of a 6.5 Creedmoor one-fire cased without annealing. You can see the static force increasing to about 40 pounds. Then you'll see the drop. Here's the kinetic drift force. We reach a maximum up here at about 107. You'll see a small drop here. What this means is that the bullet's gone past the neck by just a few thousandths, and then here's where the drift bottoms out. This is the insert depth, 302 thousandths from here to where the drift bottoms out. Here's the seating profile for the 6.5 Creedmoor case once fired that's been correctly annealed. You'll notice the DFS is down to 28 from 40. Clean break. We get a good dynamic drift force. We get a max here that drops down from 107 for the unannealed case to about 70, 79 here, and then you see where the drift bottoms out. This is pretty typical. If the bottom of the bearing surface is flush with the neck, you're not going to see a drop down to FK. And here's the insertion depth here. This is a seating profile from the same batch of cases we showed in the previous slide. So this has been properly annealed. But what we've done is do what we call overseating. So instead of the Cole going to 2.8, we set the bullet to seat much further than that to make a point. You can see DFS breaking here, DFK, breaking up at 66 pounds. But what you'll also notice now, a drop down to the kinetic force of friction. So the bearing of the bullet is well past the neck and just sliding further into the case. And you can see, instead of normally seeing this about 300 thousandths, we've had an insert depth of 375 thousandths. You're normally not going to see this, but we just wanted to make up a case here to show folks so they'll understand where that measurement comes in. Having the seating profile is a good start, but we want to measure that also includes neck geometry. So what we're going to do is model the case neck as a cylinder. We can start with SAMI spec to get our needed measurements. But in the model, we want to include variables for pullet diameter, wall thickness, and trim length. An important thing is the kinetic coefficient of friction. This is an important parameter, but for the work we're going to do here, we're just going to set it as a default to 0.3. We need to get the kinetic force of friction, and you can get that from overseating, and we've illustrated that. And we'll illustrate also how you can do this with what's called long for caliper. Once we have that information, you see how this is laid out here. Here's the key measurements. What we want to do is compute hoop stress. We need to use what's called a thin wall assumption. There's two categories for the hoop stress, thin wall and thick wall. The interested viewer can research this out for themselves. But basically, you want to know if the wall thickness is thin relative to the overall thickness of the container. In this case, with the rounds we're working with, like 223 and 308, that percentage is about 9 to 12%. So we think we're very safe accepting the thin wall assumption. We need to use the normal force to calculate internal pressure calculations, and we get that from the coefficient and the kinetic force of friction here. So once we can compute seating pressure and we have force over area, we then have hoop stress. And as you can see where this comes from, simply the hoops that used to hold barrels together. It's worth repeating that our goal here is a reference measurement. We're really not doing design parameters. We're looking for statistical data that helps us with making comparisons in our reloads. So we're pretty comfortable with using hoop stress for this calculation. As a case study, let's take on a common problem, and that's trying to determine if the case neck has been properly annealed. If you're using flame and induction methods, you might think about looking at the glow of the case, or looking at using temperature indicator liquids. And what about molten salt baths? You're not going to get a glow of the case, or is it advisable to put organics into molten salt baths? Maybe consider outsourcing, just sending your cases to a trusted supplier and then have them doing the annealing. And then maybe just using new brass all the time. Well, if you're going to do annealing, you'd like to know if it's done correctly. So there's a couple of measurement options. One of them is to measure microvickers hardness, HV, using an instrument a lot like this tester here from Bueller. You're typically going to be over $10,000 to get a system like that. Another option is to look at the compression and tension of seating and having bullets coming out of cases. Well, for that you use universal testing systems, a lot like these very nice unit from Instron. Well, can PounderPress be used to tell us something about annealing? Let's check it out. Let's set up a study for annealing with 223 Remington cases. First of all, the baselining technique we use for cartridge case preparation, please consider looking at that video we mentioned earlier. We're going to have three groups. Once fired cases without annealing, what we call our small flame annealing technique, which is just a torch system. We be on the lookout for a video on that. And then we'll also over anneal cases. We'll prime and charge them and use the PounderPress workstation to seat the bullets. Then we'll analyze the data. We'll prepare the seating profile plots. We'll look for the kinetic force of friction, compute seating pressures and hoop stresses, compare the groups and draw conclusions. Here's an example seating profile from our Group A. Once fired, no annealing. DFS around 42 pounds, DFK around 77 pounds, and then you'll see the coefficient of friction here at about 68 pounds. You notice a very distinct plateau here, and that's because we're seating a 75 grain bow-tail hollow point. So this is what we call long for caliper. So a lot of the bullet bearing surface has now slid into the case. Here's our insert depth, and notice that the allowance for this sample is 3 thousandths. It bears repeating that firing and resizing cold works the brass. So you're going to need higher DFS and DFK forces. We'll compare this to anneal cases here in a moment. Here's an example from our Group B, properly annealed once fired. DFS is down to 26 from 42. DFK is down to 47 from 77. And FK is down to 39 from 68 before the drift bottoms out. Here's our insert depth, and this is also with an allowance of 3,000. Annealing softens the brass and increases the ductility, so it's not unusual to see DFS and DFAs coming down. We're going to talk more about that statistically in just a few moments. Here's an example from our Group C, over annealed. You'll see DFS is now down to 15 from 26, DFK is down to 33 from 47, and the FK is down from 39 to 29. And you'll notice this profile is very rounded and very flat. So we're still at the same allowance of 3 thousandths. But what's happened, we've had too much heat for too long, and this creates grain growth in the brass. In the material sciences discipline, this is called the loss of engineering property. For us specifically, we end up with a very, very soft gripping of the neck onto the bullet, which is a undesirable property. So here's a good clear example of what happens when you over anneal brass. To compute hoop stress, we need to get the normal force. We get that from the kinetic force of friction. We've showed you can get it from either overseating or else long for caliper. But there's a relationship between the drift force and the kinetic force of friction. These are the groups that we just completed. Down here is over annealed. This cluster here is properly annealed, and this long arrangement right here is from once fired, no annealing. So what you can see statistically, we're looking for a tight group, which will help give us more consistent shot-to-shot performance. It's also interesting to notice this dispersion here is a very broad range. All these again are just single-fire brass. And so what we want to do is get a very consistent value for hoop stress, and we like a nice tight cluster to give us the best shot-to-shot performance. Here's the equation between the two, and you can see from R squared that we have a very good fit. Here's a summary of our tests. Groups A, B, and C. The allowance is 3 thousandths in all cases. Here's been the annealing. You see the drift force kinetic, the average kinetic force, and then we can easily determine the normal force, which then gives us hoop stress. Here's standard deviation of the hoop stress. So what we're saying is that when something isn't annealed, you're going to be up around 8,000 psi, properly annealed around 5,000 psi, and by the time you get down to 3,700 psi, you've probably over annealed. So for this recipe, for the 223 Remington, anneal before full length resizing, accepting the kinetic coefficient of friction of 0.3, we want to aim for a hoop stress of around 5,000 psi. One final thing is this column here. One of the techniques we use in analytics is called statistical graphics. What we mean here is that sometimes you deal with complex relationships, and a picture's worth 1,000 words. So although we like to get nice simple numbers, sometimes how something looks is very important in the graph. So what we kind of position here is this is like the beds in the Goldilocks and the Three Bears. The Papa Bear's bed is just too hard. The Mama Bear's bed is just too soft. But the baby bed is just right. So exactly what is this allowance we've been talking about? Well, you might know it as neck tension. Neck tension is the dimensional measure. It's not a real measure of tension, force, stress, strain, or pressure. And it doesn't include important metallurgical properties. We just demonstrated that. It also doesn't have anything to say about important tribological properties either. So we think it's a rather poor proxy for what we really want to know, which is to understand the seating force of the bullet, the ability to measure and control this property, and why do we want to do that? We want more control over the reloaded round. We want to understand and improve and control bullet release and firing, and this helps us make better reloads and more consistent round-to-round performance. Let's take a look at what we've learned about seating from the standpoint of materials. Let's do the bullets first. In this table, we look at the factors, what kind that it is, what would be typical values, what kind of treatment we would work with in reloading, and what we mean by a control tier is just how much control we have over that. With bullets, we don't have a lot we can do. Note here that cast or coated lead alloy bullets are kind of a special case, but normally the diameter is locked in by what you're going to load. The covering the bullet, that's locked in, very hard to change that. The smoothness, the tribological type, these are controlled by asperities, which are fractal properties. This is dealt with by polishing and coatings. That's very hard to work with. We're not talking about moly-coated bullets. If you want to use those, that's fine. What we're talking about, if you were to try to control that coating, that's pretty challenging. And then hardness, which is a metallurgical property, again, that's spec and you take it as delivered, and that's very hard to do anything about. Again, in the case of cast lead, you could certainly harden lead and such like that, but all of the full metal jackets and such, there's not really much you can do. On the cartridge side, we have a lot we can do. We got wall thickness, which is a dimensional property. There's a nominal value. We can do turning of the wall. That's we do that all the time. It's a little bit more work there, but easy to control. If you take a look at the neck length, this is again a spec, but we can do that with trimming. That's easy to do. The allowance, the old neck tension measure, that can be done with sizing. We do that all the time. And then with smoothness is a tribological property, and again, we deal with asperities and coatus and polishing. And of course, you could certainly take a Dremel with a buffing wheel and polish the neck, but you're really not providing a real good control over that. And then hardness was the metallurgical property. We have a number for that. This is done with annealing, and we put it at the mid-tier, maybe just a little bit of a plus because you have to do a little bit more to know if things are correctly annealed. But we do have a lot of control over the cartridge case, not so much with bullets. Here's our bullet seating proposal. PounderPress allows us to replace the old notion of neck tension with what it really is, allowance. We're able to measure the drift force kinetic and the frictional force and easily compute the normal force, and this lets us easily get a hold of hoop stress. So in combination with case prep baselining, certainly being attentive to processing, cleaning, lubrications, dimensional treatment, resizing, we're very comfortable with that, metallurgical treatment, annealing, and tribological treatment, stay tuned, that's still a work in progress. So if we were to summarize what these measurement metrics are, let's take a look. Insert depth, dimensional, that's a spec. We can easily adjust and trim seating depth and trim the brass. That's easy to do. The allowance, that's going to be easy to do. That's done with sizing. We do that all the time. Seating force, the drift force kinetic, done with seating, that's easy. Frictional force, we can easily get that as well. That's done in the seating step. And then with hoop stress, which is a pressure, PSI is the measure, we can compute that, and that gives us a result that we can measure and control. This completes our presentation. I'd like to give a special thanks to Bryce Sturdivant, PhD, for his contribution to this work. And as you're thinking about subscribing, please take a moment to look over these important notes and disclaimers. They're here for your protection and ours. Thanks for watching. See you soon.